Awesome. Would you like to introduce our speaker as the host? Let's wait a second. Let's make sure that I stream starts. It's went to someplace. Okay, it seems like we are live.
Okay. Should I start?
Yeah.
Okay. Hello, everyone. Welcome to today's Safari Live seminar. Today, Jonas from TU Graz is a PhD candidate working with Professor Daniel Graz. He will be introducing the recent works on RowHammer, and he will be talking about two works mainly: CSI Rowhammer, which is about memory integrity, and press hammer, which is a real system attack that leverages RowPress. So yeah, Jonas, please.
Thank you for the great introduction. As already said, I'm Jonas. I'm a PhD candidate from the Graz University of Technology, and I focus on RowHammer, attacks and mitigations, side channels in general, and microarchitectural attacks. Let's jump right into RowHammer. I think most of you know what RowHammer is, probably. So I'll just have a short summary here. So this is typical double-sided RowHammer. What we do here, we have these rows in the DRAM. Okay, my laser point isn't really working. We have these rows in the DRAM, they're aggressor rows. And if we access them really quickly, a lot of times, so the actual activation count is 10 to 100,000 times, we access these rows, we can see bit flips in this victim row in between, which means that some bits can flip, and this is bad because this is victim row is usually memory that we do not control, that we should have no access to, and that we should not be able to change. So this is RowHammer. We access these rows as quickly as possible. There's also RowPress, recently found, and it works similar, but there's one big difference. It doesn't try to activate rows as quickly as possible, but it tries to keep the row open as long as possible. This means by accessing one of the aggressor rows, it's copied into the row buffer, and then multiple offsets in the row buffer are accessed to keep the row open. Then the row is copied back, and the next row is again kept in the row buffer as long as possible to keep it open. And we now did this less often, as you could see. And again, we see bit flips in this victim row in between. And the interesting thing here is that this flips different bits than RowHammer because it's based on a different physical effect. The reason for why bits flip is different between RowPress and RowHammer. So we see different bits to flip in the DRAM. If you want to do this from a CPU, it's slightly different. There we have a memory controller that we don't like, but we have to deal with it. And it has to adhere to DRAM timing limits. And one of these limits is that a row must not be open longer than 9 times the T roughly, which is 7.8 microseconds. So there we cannot keep a row open as long as possible, like as long as we want, but maximum this time here. And because of that, it works not so well than when we would do it on an FPGA. Okay, this is RowPress and RowHammer. There's also single-sided RowPress, where we just keep a single victim row open as long as possible. One single row, again, we copy it into the row buffer by accessing it, and then we keep it open very, very long. And then after some time, neighboring victim rows flip. Okay, single-sided RowPress. But wait, there was a paper in 2018, this one, another flip in the wall of RowHammer defenses. And what we found here is that when we access a single row very often, not like RowPress, keep it, like our goal wasn't to keep it open, but to access it again and again. So we access it and we access the same offset again and again. And then we also see bit flips. This was really unexpected at the time. But it looks a lot like RowPress. It was 5 years prior. So what's going on here? Our hypothesis back then was, 5 years ago, that it's the memory controller, that actually what happens is the aggressor row is copied into the row buffer. And because the memory controller employs a closed row policy, it actually doesn't keep the row open. So as soon as we read this one offset from the row, it's copied back into the row. And then we access the row again. We access it from the row buffer and it's instantly copied back. So this is actually RowHammer because now this row gets moved back and forth between the row buffer and this aggressor row all the time. And we see bit flips. So this was the hypothesis 5 years ago. Case closed. We had a reason why this works. Yes. So, but was this really a reason? Is RowPress actually one location RowHammer? And this didn't we just know 5 years ago? And now this RowPress paper comes out and tells us that our hypothesis 5 years ago was wrong. So were Cruz et al. Wrong all along? This is what we tried to figure out in our paper Press Hammer. So we tried to compare one location RowHammer and RowPress and wanted to see if those are actually the same effects and that our hypothesis was wrong. So we made a simple experiment there. We know that RowHammer and RowPress are caused by different physical effects. So different bit flip locations are flipped when using RowHammer and RowPress. So if we now perform RowHammer and RowPress on the same DRAM DIMM and compare the locations where bits flip, there are two options. If the same locations flip, then one location RowHammer actually always was RowPress. If not, then our hypothesis from 5 years ago was correct, and it's actually this closed row policy from the memory controller that causes one location RowHammer. And then we wanted to draw this beautiful matrix where we compared like how many locations are the same between the different sets. So we tried double-sided RowHammer and one location RowHammer and double-sided RowPress and one location RowPress. We had many DIMMs where we tried this on, and this was the first sad thing that we found is that RowPress in our case, and also one location RowHammer and one location RowPress, we were only able to get bit flips on two DIMMs that are of the same type. And it's actually a quite old DIMM. I think it's from 2017. And I think that's similar to also the RowPress paper. It was also quite old DIMM. So our data set wasn't too huge. We wanted to see RowPress on more DIMMs, but this is all we got. And then we drew the matrix. And what we wanted is we wanted to have like a clear signal on like either the RowHammer bit, the one location RowHammer bit flips are the same as RowPress or they're different.
So first I need to ask, I guess, like,
yes.
Do you want to get questions at the end or?
I think it's quite long. So if you have questions, you can ask in between.
Okay.
Otherwise, yeah.
Can I ask
yes.
one thing first, like not relevant technical stuff? The camera is sort of blocking the slide.
Ah, should I move it?
Can we minimize it?
I could also like, I guess down here, that's, oh, I can also hide it. Yes, you know how I look like, right? Perfect. Okay.
Yeah, my question was from the previous slide.
Oh, now it's wrong. Selected.
Common bit flips, yeah.
This one? Yes. So that's not the common, that's just where we reproduce bit flips in general. Yes.
So what does that mean?
When we didn't see any bit flips when hammering double-sided, we didn't even try one location because we typically see less bit flips when doing one location. And for timing reasons, we didn't try them.
Oh, okay.
Yeah.
Are the positions of bit flips consistent?
Yes. So between like if you do a RowHammer attack multiple times on the same memory region, you find bit flips in the same locations consistently. And if you do RowPress, you find also consistent bit flips, but at different locations. That's yes. This is basically where this experiment is based on. These are the number of bit flips you got. So here we see that double-sided RowHammer definitely works best. We got most bit flips when RowHammering double-sided. Double-sided RowPress also works pretty well. Then we have one location RowHammer, which is quite interesting. We saw many bit flips there. And one location RowPress didn't really work well. So there are almost no bit flips. Then we drew the matrix and we got this, which is not really what we expected. So what we see here is that like the overlap between one location RowHammer and double-sided RowHammer is around 50%. So 50% of the bit flip locations overlap and 50% are unique. And we didn't really know what to do with that result. And the same is for double-sided RowPress. We also see some overlap, but they all overlap with, so all the RowPress results overlap with RowHammer. And in between RowHammer, we only see a 50% overlap. So, yes.
One question. What's the difference between the RowHammer, like one location RowHammer and one location RowPress in your experiments?
It's the number of accessed offsets, actually. So let's go back quickly. How far can I go back? So here we only access this offset because this is what we did 5 years ago. We only access the first offset in the row. And for RowPress, what they did is they accessed multiple offsets in the row. So this is the only difference. And this is why we thought it shouldn't make a difference. It should be the same result, like the same number of bit flips, same locations, because of our understanding of how the DRAM works, this shouldn't make a difference, but it did. And yeah, the sad thing is we don't really know why. It's pretty inconclusive, the result. Our theory is that actually one location RowHammer can induce bit flips through both effects. Because of this memory controller that has to close the row after 9 times TRFE, we still perform RowHammer. It's slower RowHammer, but we still perform RowHammer, but we also do RowPress by keeping this row open quite long. And so we think that one location RowHammer can actually cause both effects, and we see bit flips of both sets. Yeah. And then we built an exploit with that because exploiting is always fun. And we called it press hammer because we are not sure if we're now actually RowHammering or row pressing or doing both. So this is press hammer, our newest thing. And I just moved this mouse pointer here. And this is how we do it. First, we have to find a complete DRAM row. This is new to what we had to do with RowPress. Then we template this memory for bit flips. As I said previously, these bit flip locations are repeatable. So by just allocating a huge chunk of memory, going through it and searching for bit flips, we are sure that then in the exploit phase, this bit will flip again because they're repeatable. Then we spray page tables. So we use the page table exploits, initially shown in 2015. I will explain this shortly. We flip page tables and profit. We get full access to the physical memory. Okay, we have to find a complete DRAM row. A DRAM row is typically 4 kilobytes large, and a memory page that the operating system uses for paging is typically 4 kilobytes large. But sadly, there is no one-to-one mapping. It's not like that one memory page is also one DRAM row, because there are these DRAM mapping functions here, quite complex. This one is for Sandy Bridge, if I remember correctly, and they map the physical memory addresses to the actual locations in the DRAM. And what this looks like for example, this addressing function is that we have 4 physical pages, like memory pages, A, B, C, D, and this is one DRAM row. So this is how they are located in a DRAM row. And now we have to find this to be able to perform a proper row press attack, because we have to access multiple offsets in this row. And this is how we do it. We use so this is how this looks like now. We have these offsets of the physical pages in this DRAM row, and we want to find all the offsets. And we start with any page, with any 4 kilobyte page we get, and it's like this in their memory. And then we allocate the second DRAM page quite far away, so an offset of 100 pages. So it's definitely in another row in the same bank. And what we know is that we want to have an offset that's in the same bank. And this means that we want to measure a bank conflict with X. So if we now go through the memory and check if we see a bank conflict with X. If we, for example, get this page, we see a bank conflict. Perfect. But this is actually not the page that we want because it's not in the same row. So there's a second requirement. We want no bank conflict with A. So G is not a good candidate because we also have a bank conflict with A. And then we find this page, and that's great because here we have a bank conflict with X and no bank conflict with A. Then we go to the next offset, again, search through the memory. We find, for example, this here, no bank conflict with X because it's on a different bank. So not the correct page. But it has a bank conflict with, no bank conflict with A, which is useless. And then we find this page again after some trying. Again, bank conflict with X, no bank conflict with A. And this is how are we able to build the full row in a DRAM without knowledge of the DRAM addressing function, without knowledge of the physical addresses, so completely unprivileged, which is the requirement for our exploit. Yes.
So does it help you, how can I say that? So you don't need huge pages or anything.
Exactly. We don't need huge pages. We don't have to know the addressing functions. We have no knowledge. We just allocate some memory and then go through it and use this tunneling side channel to build this row.
Do you just go through the whole virtual address space?
No, that's usually not required. So what we did is we took the page A, because the good thing is if you allocate a lot of memory, at some point the operating system gives you quite consistent chunks of memory.
I see.
So we just allocate the gigabyte, we scrap the first 500 megabytes, and then we start looking, and then we are pretty quick at finding these.
I see.
So we take one page, then we try the page above, below, like of virtual addresses, and we do this a few times, and then we find this quite consistently. And they also have numbers here. Yeah, and then we find D and so on. This is the number of measurements we do for the bank conflict side channel. So we do like, if you do 500 measurements, for example, for each page, it takes us 45 milliseconds to build a row, for example. So this is super quick. And we find pretty much all offsets. And of the 128, for example, 125 are correct. And this is totally enough because we don't need all offsets to do RowPress. So this works extremely well and quick, which is nice for our exploit. Yes, then we do the memory templating. So first we ensure that RowPress bits are like RowHammer bit flips repeatable. In the paper, they turn off the cache line prefetcher, which is only possible with, is that correct?
Yeah, I want to provide a correction. So
yes,
in the real system demonstration of the RowPress paper, we do not turn off the prefetcher for demonstrating the bit flips. We
perfect.
We only turn it off when we want to show that if you access consecutive cache lines, then you have longer time that the row stays open.
Okay,
so
okay.
For actually inducing bit flips, we do not turn off the prefetcher.
Perfect. And you maybe use the same trick to just shuffle the offsets because this worked perfectly for us.
Yes, it might also work, but there can be more sophisticated prefetchers.
Yes, maybe detect that.
Yeah.
Maybe. We just shuffled the offsets that we access, and then the prefetcher doesn't get in the way. So that's perfect. And then we template the memory for 10 exploitable bit flips because there's in the later stages of the exploit, there's a chance that not every one of the locations work. So just having 10 at hand gives us a really high probability for it to work.
Is it like 10 bit flips in the whole row?
In the memory we template. So we find 10 rows where we find bit. We look for 10 rows where we find any bit flips, and this gives us a high chance. Okay. So how does the actual exploit work, the page table entry flipping? Let's take this example. There's virtual memory on the left, the one where the process works on, and there's the actual physical memory on the right. And the mapping from virtual, I think as all of you know, from physical works through page tables. So I have this drawn here, just one level of page tables because it's easier to draw. We have this virtual address, it goes through the page table, and that actually translates it to a physical address where the physical page is. What you do in our exploit is, we now fill the whole memory with page tables, which gives us a pretty high chance that our page table is next to one of our aggressor pages, aggressor rows where we found the bit flip. So we put this there, and then we hammer or press hammer this page. And there's a chance that this pointer actually changes. So currently it points to physical address 1 here, but because of the hammering, it now changed where it points to, and now it points to a other page table of the same process. And now we as an attacker have write access to one of our own page tables and can make this physical address 2 point wherever we want it, because we can just write the page table entries. So we can just now shift this physical address around and read the whole physical memory and write the whole physical memory. So this means we have all the permissions on the system that we want. We can change kernel code, read kernel data, and so on. Yes, let's shift this around. And this worked pretty neatly. So we tried the exploit 5 times on the same machine. First time it didn't finish because we did not successfully hammer a page table. So this is where the luck comes in. We have our set of exploitable bit flips that we know of. We spray the page tables, and then we press hammer these offsets. But sadly, we didn't find any bit flips in our page tables. So it didn't work. On the next try, the exploit finished in about 10 minutes. Again, did not finish. We hammered the page table. So the hammering was successful. But sadly, it didn't point to another page table. So this step where it then points to another page table, it just pointed to some garbage data and not one of our page tables. Then we run it again, 10 minutes, and again, and it finished in only 5 minutes. So based on that, a bit better than 50% success rate. And the good thing is, in most cases, you can just run the exploit again. So that's pretty neat. So we showed that press hammer, RowPress is exploitable. And I think the other great insight for commuter security actually is this table here, that it seems like the current mitigations hold up against RowPress pretty well, because all these newer DIMMs here were not affected by RowPress. They all come with TRR, and it seems like that the TRR thresholds are low enough so that even the RowPressing that doesn't activate the rows as quickly as possible, but still in a pretty quick manner, is enough for TRR to trigger and prevent these bit flips. So yes.
So during the attack, did you measure the access time for each of your reads?
We did measure them, but not publish. But the data is somewhere.
Okay, I was curious if like some of them are actually activating row again, or you keep access in like columns in the open row. Does that make sense?
Ah, you mean for every single access to time?
Yes, yes.
We don't have those, sadly. But it would be interesting, yes. But we did one location RowPress for the exploit. So there we expect that the row to be open most of the time, right?
Yeah, but if it's assuming that it's open all the time, then it shouldn't trigger the TRR mechanisms, right?
Yes, but the thing is, that's where the memory controller comes in, that has to close the row after a certain time.
Yes. And
this is what all the memory controllers do.
Okay.
And this is why we probably see also RowHammer bit flips.
I see.
Yeah. So in that case, RowPress seems to be mitigated by current mitigations, especially TRR, which is great for our security. But we were not always so lucky. Actually, 4 years ago. And the problem why this can happen is that mitigations, RowHammer mitigations, often focus on characteristics of RowHammer. For example, that bit flips are infrequent. When RowHammer was first discovered in 2014, it was, the manufacturers just came by and like, okay, this is not a big problem. First, no one can exploit that. No exploits were shown back then. And we just doubled the refresh rate, for example. Or we have error correcting codes. They can correct the single bit flips. This RowHammer problem easily corrected by ECC. Yeah, this catched by hardware, perfect. Increasing the refresh rate. So many manufacturers just released BIOS updates, increasing the refresh rate from 64 to 32 milliseconds, perfect. RowHammer solved. as we all know, this is sadly not the case. RowHammer bit flips are way more frequent, and these mitigations did not hold up. Another characteristics was then like the next level of mitigations that were proposed are extra detectable. We can, for example, just use performance counters where you see the number of cache misses. If you have a program that causes a lot of cache misses on the same address, this program is probably rowhammering, so just kill the program. Yeah. This is what they tried, for example, with Anvil. Yeah.
Jonas, we have a question from YouTube.
Mm-hmm.
So there's a question from Reshma. As far as I understand, we need to modify some specific bits of the page table entries to make it point to a different physical address. How do you control which bits the hammer or press and flips?
This is a really good question. So the question was, how do we control which bits in the page table to flip? We cannot control that, but we can kind of look out for it in the memory templating phase. So the exact bit that flips is fixed for a specific offset, because that's some weaker transistor probably that just flips more easily. So in the memory templating phase, we don't look for any bit flips in the row, but we look for bit flips in a specific offset where we know that the page frame number will be. So in the memory phase, in the memory templating phase, we can already at least ensure that the offset is in the correct location. If it works at the end, we cannot control, but this is what we do.
Yeah, thank you.
You're welcome.
Yeah. By the way, I also have a question regarding like one of your earlier, let's say, hypotheses on why, let's say, we're not seeing double-sided RowPress working on as many modules as in double-sided RowHammer. And then, if I remember correctly, you said probably like the newer TR implementations, they have a, let's say, like row activation threshold much lower.
There's another option.
Yeah.
Where they maybe includes activation time.
Yeah, maybe,
yes.
maybe.
Yeah.
We
don't know. I think Samsung has some paper where they talk about that. So the DSAC paper.
Yeah, the
yes.
DSAC paper.
So they don't only count activations, but if a row is open for longer, they include that in the counter. Maybe count up a little bit more. Yeah.
Thank you.
Exactly.
I would like to challenge this.
Yes.
So I understand that the access pattern is a bit weird, but we could observe some similar access patterns done by benign workloads as well, right? So
exactly.
Did you actually like evaluate, observe some benign workloads access patterns and see like how similar are these? Because like if you just like stop suspicious applications, kill them, it's some sort of like a harsh punishment, right?
Yeah,
so,
that's the thing. You don't have to stop applications. Of course, you can just also manually access victim rows to refresh them, for example, from your kernel thread or whatever who does that. You're totally right. I'm also showing this because I want to show you that this doesn't work. Because there are more reasons why this cannot work. For example, in the one location RowHammer paper I showed before, we hammered from SGX, from Intel SGX applications. And if you run code inside Intel SGX, you can actually not see the performance counters because the SGX hides it from the operating system. And if you have defenses like that, you just put your application into SGX and that's it. So this is what you showed in 17. So also this characteristic actually is not really true, sadly. And there's the third characteristic where most mitigations were based on, that flips only happen at distance 1. So only directly neighboring cells are flipping. And then people proposed different mitigations based on that. One, for example, was to introduce guard rows. So for different security contexts, for example, user space processes and kernel processes, you just put guard rows in between in the physical memory where you don't put physical pages. And for example, this one paper, SAPRAM, put swap space there, integrity protected swap space. So even if you hammer it, it doesn't break and you're fine. Celly doesn't really work. There's another mitigation, and this is probably the most well-known and also the one that's employed in all current DDR5 chips. And I think it was not mandatory in DDR4, but all like latest gen DDR4 DRAM has it as well, is target row refresh, TRR. And it works like that. Whenever a row is accessed, a counter just counts the number of accesses. And we have these counters here on the right. And after some time, the counters are full and the memory chips comes in and refreshes all the neighboring rows to keep them safe. It's a great idea. And it mostly broke for DDR4 because the implementations were not perfect, because DRAM manufacturers didn't want to make a counter for each row. They tried to do some fancy trickery to only have a few counters and then trying to detect which are aggressor rows and then only have to count these and stuff like that. So they did a lot of stuff, and then Trespass and Blacksmith broke all these schemes. So TRR basically broke because of bad implementations. So would a perfect TRR, so a counter for each row, fix RowHammer? The sad answer is no. And this is what we showed in the half-double paper, half-double RowHammer, hammering from the next row over. And the effect that actually researchers from Google first observed there is that you can do something really funny. You can actually use TRR, the mitigation made to prevent RowHammer, to enable RowHammer from a higher distance. So what we do for a half-double RowHammer attack is we access these far aggressor rows, we call them, that are one row further out. We access these again and again. And after some time, TRR comes in and refreshes these near aggressors. The one on the bottom, of course, also the one on the top, but it's not relevant here. So it accesses these, it refreshes these. And we do this more often. And TRR comes in again, TRR comes in again. And then this victim row in the middle flips. So for a reason we don't know, sadly, these very infrequent TRR accesses, it can be 1 in 10,000 accesses, help to transport the charges from this far aggressor to the victim row. And this actually causes the victim row to flip. So even a perfect TRR implementation actually helps us to hammer with the half-double effect. This is bad. And this is also exploitable in the wild. We showed that by attacking a Chromebook, where we again used the page tables as an exploit primitive and did some bit flip verification using speculative execution to make it more robust. And there we were able to exploit the Chromebook from an Android app in less than 40 minutes with the half-double effect. Yes.
So we have a question from Chinsai. So why the page table entries are often near the data they corresponds to? Is it always the case across different operating systems?
So typically not. So the operating system tries to put the page table somewhere else than the data. The simplest thing to do, and also what we did here, is just map a file again and again in virtual memory. This creates a lot of page tables. And at one point, if you create enough page tables, the operating system has to put page tables next to the data. There are also memory massaging techniques where you can actually, because the Linux memory allocator works predictable, so you can actually massage it to put one specific page table exactly where you want it to be. And I think this was it was a ROM exploit in Android. I don't remember the name, but there they did the really, really advanced approach of memory massaging to put the page table there. So typically not, but you can force the operating system to do that. So we exploited that. And this is a problem. So we have these 3 characteristics where basically all RowHammer mitigations are based on. And apparently this does not work. Basing RowHammer mitigations on specific characteristics, thinking about RowHammer too much when implementing RowHammer mitigation, apparently is a bad idea. And we tried to rethink RowHammer mitigations. We wanted a generic approach to data integrity protection. So don't care where the bit flips come from. It could be RowHammer, RowPress, Cosmic Rays. We don't care. We just want to protect data integrity. And this is how we came up with CSI Rowhammer. So we have this generic approach to data integrity protection, and we just detect all data integrity failures using a MAC, a message authentication code. And then the problem with MACs is that they can't do correction, so we do a best effort correction. This has the this means that we cannot correct all bit flips. So in the worst case, we have a denial of service attack that an attacker can perform. So it can never exploit bit flips because we always detect them. But if we cannot fix bit flips, in the worst case, we have to restart the machine or something like that. But there are never exploits. Denial of service is the worst thing that can happen with this approach. Yes, exactly. And this is our paper, CSI Rowhammer, cryptographic security and integrity against Rowhammer. And I just want to start with a beautiful animation I made. This took me way too long to show you how this works. So here we have the DRAM on the top. And here we have the memory controller of the CPU. And this is where we perform the first changes. So we have this MAC computation unit in there that computes a MAC of the data. So it takes in the data, it computes a MAC, and it writes it to this additional chip here. So this is ECC RAM. ECC RAM comes with an additional chip for actually ECC codes, but we repurpose that for our integrity information. So on every writes to the memory, we write the data, and we also write the MAC and some parity bits. And then when we read, we compare the computed MAC, the one we compute again, with the stored MAC. And of course, if they're the same, we are pretty certain that the data did not change. If the MACs do not match, we can perform a single bit flip correction directly in hardware. If we have more than one bit flips, if this hardware correction didn't work, we delegate to the operating system, to the software. And this has some nice advantages. So we introduced a new exception, an exception handler for that exception. And our first try is correction as a search. I will talk about that in more detail in a second. It's basically a brute force search. Flip all the bits until the max match. But it is not that bad as it sounds. For this, we added 3 new CPU instructions actually that we use for that. And we also have an advanced correction because now we are in software. The operating system has a lot of knowledge about the data that may be corrupted. So for example, if the data that's corrupted is stored on the disk because it's just some page cache pages, for example, we don't have to correct anything. We just reload the data from the disk. And actually in a normal system, a lot of DRAM is used for the page cache, all your free RAM, basically. There's one thing left. The whole operating system and the exception handler and everything is stored in the DRAM. And now an attacker, of course, could hammer this exception handler and basically destroy the whole system. So if an attacker does this, that's bad. So we also include a small secure memory on the CPU. It's like DRAM, not like DRAM, but like caches, so SRAM. And we put the exception handler and some other stuff we need in there. So the exception handler and this correction as a search code is completely secure from Rowhammer. Okay, let's look into this in a bit more detail. This is how we store the MAC on DDR5 memory. So we have the data here. It's partitioned into 8 partitions. We compute the MAC over the whole data, and then we store 8 parity bits as well. So we have a 56-bit MAC and 8 parity bits. And this fits exactly in the space that we get from DDR5 ECC memory. So this is the MAC size is basically restricted by that, but it's enough for our security guarantees. This is how we compute the MAC. So we use this pipeline PMAC construction. We use the Karma block cipher here, and this has a 64-bit input. So these are 4 message blocks. We always take like 2 blocks, 2 of these from 0 to 64-bit blocks. We put them into one Karma block cipher. We XOR the first 3 results and then put the final result through a block cipher. The good thing about this design is that it can be parallelized quite a bit, because we can parallelize these 3 computations and only have to do the last one in serial. And the Karma block cipher for the hardware design is also possible to be pipelined. So we only need a single Karma block cipher block, and we pipeline these 3 to have really low latency. And with that, we can compute the MAC of 256 bits in 5.13 nanoseconds and of 212 bits. So this is for DDR4, because there we have less ECC data, in 6.6 nanoseconds, which is way lower than a DRAM access, which takes around 100 nanoseconds. So the overhead of the MAC computation is actually quite low compared to the memory access itself. Yes, so we did the MAC compute, we did the comparison. Now we find a bit flip, and now we want to correct a bit flip. And we do a single bit flip correction in hardware. And the problem here is that Macs cannot correct bit flip. That's like their basic principle. It's like there's no linearity. We actually don't know where the bit flip comes from. And what we do is we do a brute force search. We go through all the bits, we flip a bit, compute the MAC, compare it, flip the next bit, compute the MAC, compare it, and so on. And we use approximate equality, which sounds super bad right now, but I will talk about this. Let's take this data here, and it produces this MAC. If we find this MAC, we also let it slip. That's fine. Just a single bit. What's the chance? We let it slip. We don't have the MACs don't have to be equal. Approximately equal is totally fine for our use case. Why we have to do that? A little bit later. And we have our parity bits, and they actually introduce some linearity. They give us some hints where the bit flips probably are. Let's look at an example for the single bit flip correction. So we have a bit flip in here. This is where the RowHammer attacker was able to flip a bit. And this means that the MAC does not match anymore. The MAC is completely different. And one parity bit. This parity bit corresponding to this thing here also isn't correct anymore. So we know where the bit flip approximately is, and we know that there definitely was a bit flip because the MACs don't match. And what we can do now in our hardware design is pretty neat. We know that the bit flip is in this block. So we only have to compute these results once, and then we store them, and we don't have to compute them again. And this makes our correction pretty quick. And if we are lucky and the bit flip is in here, we actually can pre-compute these 3, and we don't have to compute them again while brute force searching. So we only change the bits in this message and only have to compute one Karma block and not these. And with this, we are able to correct brute force search 256-bit data, because we don't have to search all the 256 bits, but only 32 in 11 nanoseconds and 512 bits in 13.8 nanoseconds, which is still a lot shorter than a DRAM access. So single bit flips should actually not be detectable, or like not influence the computer's performance at all. The correct math for this is in the paper, if you don't believe me. It works for the pipeline and everything. It is quite efficient.
So this 11 nanoseconds for swapping 32 bits?
Yes. Swapping, like it's the average, so 16 bits. After 16 bits, you have a 50% chance to find the bit flip, because it's somewhere in the 32 bits. And yes, so you flip one bit, compute the MAC, flip the next bit, because the Karma thing is pipelined, because the Karma block cipher can be pipelined. And we have, for example, this case here, we can actually try one bit flip with a single clock cycle. Then we have 32 bits, so it's pretty quick. Okay, so single bit flip correction works pretty well. If there are more bit flips, we delegate to the OS through a new exception that we introduced in our design, and an exception handler that then basically does the same thing, but in software. They have some nice code for you there. So we do error correction in software now. We have this corruption exception that's similar to a page fault. It gives us the physical address in the CA2 register. We need the physical address because we cannot rely on page tables to translate the virtual address. We want to have the We want to actually know where the bit flip happens. And if you have to rely on page tables and they may be also corrupted by RowHammer, that's not good. Because we don't want to be dependent on page tables. And then we just brute force all possible flips. Using the parity bits as a guidance, the parity bits help us to know where bit flips probably are. And we want to do this as fast as possible, obviously. And we also want the codes to be as small as possible, because as you maybe remember, we put all of this code into this on CPU memory. And we don't want a huge CPU area overhead, because otherwise the paper won't get accepted. And therefore, we wanted to have this as small as possible and as fast as possible. And there is no other way than nested loops. And this is how I came up with this beautiful piece of code. And it's basically how you would write a really stupid brute force search with multiple bits. It's just nested for loops that each have their own bit flip offset. So this is how this looks like. We have a flip mask for each number of bit flips you want to try. This now includes the code for a single bit flip correction, just for completeness. And then we have this bit flip mask too, and so on. And we just flip this mask, we shift this mask by 1. We flip the bit with this mask. We compare the max by computing them and comparing them. We flip the bit back and so on. And this is how we go through all the bit flips. You have a question?
Yes. So this is a very beautiful piece of nested loops.
Thank you.
So,
thank you.
But
I'm proud.
Before coming there, so I understand that you already have the computation unit for Mac implementing your memory controller.
It's also in the CPU core.
Yes. So yeah, I'm going to question the necessity of that actually. So on top of that Mac computation, what I see here is like some shift operations, some masking, and these are very cheap operations to implement in hardware. So I couldn't understand why, like, for 1 bit flip correction, you do it in hardware, but more than 1 bit flip, you offload all that work to the operating system. Wouldn't it be faster and cheaper if you would just build more logic in your memory controller and do all the computation there for like 2 bit flips, 3 bit flips, 4 bit flips?
Yes, could be the case. What we wanted to show here is that maybe this brute force search is not the best solution. And if you go to the operating system quite quickly, it can figure out another way to get this data maybe. As I said, if you have data that's stored on the disk already, because it's just a page cache, you don't have to do any brute force searches at all. And then you can just reload the data from the disk. And so what we, of course, one could now argue, would it be more efficient to do like up to 3 bit flips in hardware and then delegate to the operating system? Or like what's the good threshold? Like how many bit flips do you want, or maybe take another solution than the brute force search? That's a good question. You know what I mean? So yeah, it doesn't have to be that already for 2 bit flips, it makes sense to delegate to the operating system. Yeah. But at one point it makes sense. And this is why we chose this solution, and we took a single bit flip in hardware, because it was like not the main contribution of the paper, basically. And at one point you're more efficient if you do it in software anyways, because of the other solutions you have, or the other options you have for correcting the data. You could also have like a hybrid approach where you have like the memory controller have brute force search the data. In the meantime, it tells the operating system, hey, you want to check if you could also reload it from the disk. And like do this in parallel, of course, would be possible. If you want to write the follow-up work, welcome. Yeah, but we chose to do this in software here. And now let's say we only want to do 2 bit flips, right? We have to go into this loop somehow, because in here we check a single bit flip and then 2 bit flips. How do we do that? We have this go-to labels here before every loop. And what we do with that is we can jump in here, then execute this loop, and then jump back out of the nested loop here. And this is how we are able to first try 2 bit flips, then 3, then 4 with 1 nested loop, just a single piece of code. And this is where we have all these labels for like also the parity bits out here. That's the logic for the parity bits. That's described in more detail in the paper. And then all the labels for the number of bit flips you want to try. Then we use this beautiful non-C standard double end syntax to get the address of a label to dynamically jump in C code, which the inventors of C didn't want us to do, but it works. And the Linux kernel isn't C compliant anyways, so great. So yeah, we built this code and we actually fit all of this code in like 1.5 kilobytes of machine code, so less than a page, which is pretty nice. So this is the correction as a search. But, oh yeah, the CPU instructions, we have those as well. We use these for three things. We have a CSI Mac instruction. That's the one that actually computes the Mac, because we want, yeah, the hardware to do that. Then we have a CSI load instruction. That's important because we want to get the corrupted data from the DRAM. And if you would do a normal load, the memory controller would check if the Mac is correct or not. And with this, we kind of can get the corrupted data without the memory controller checking the data, because we know that we use it for correction. And this one is to write the data back. And it has some, it checks the old data before to have some race conditions not happening. Also detailed in more, explained in more detail in the paper. Some edge cases we corrected there. And now we want to know how long does this actually take? How long does it take to run this huge loop, like this 8 times nested loop doing the Mac computations? Because this should be a kind of reasonable number. And how we did that is we first calculated the number of Mac computations that we probably need, like the average number of Mac computations. For example, for 7-bit flips, we have to do this many Mac computations. And then we just ran this loop on real hardware. No, first we took the number for the Karma block ciphers and calculated how long it takes to do this many Mac computations. So this takes around 7 minutes for 7-bit flips. And then we ran the loop for this many iterations on real hardware. In our case, 3 CPUs. And our reasoning was that the loop and the Mac computations actually run in parallel on modern out-of-order CPUs. Because the Mac computation is one port, the loop is another port. So these 2 times of the Mac computations and the actual loop runtime don't add up because they run in parallel. And running this loop gave us a quite interesting result. Like 3 years ago, the Apple M1 is incredibly fast. Running the same loop for 7-bit flips took 2.3 minutes on the Apple M1 and around 10 minutes on state-of-the-art Intel and AMD CPUs back then, which is quite insane. So the Apple M1 is actually bottlenecked by the Karma block cipher performance along with latency. All the other CPUs back then were actually bottlenecked by the time it takes to run the loop. But I think at this point, this should be faster. It would be interesting to run the code again on modern CPUs if they were able to keep up with the Apple M1, at least a little bit. But yeah, that was a wild result, 4 times as fast for a simple loop iteration. We expected the high number of registers probably being the case, because we have quite a few variables here for all the loop counters and so on, and this flip mask and everything, and the ARM just has more registers, and this probably cost us great results.
And you didn't do any tricks about like offloading this to an accelerator in one chip?
No. It was C code compiled with GCC, and that's it. So huge difference there. But yeah, probably the higher number of registers, and of course, just the Apple M1 being an amazing architecture. Yeah, and this is how long it takes. So single bit flip, we have the hardware here in around 10 nanoseconds. We also collected data from different papers looking at ECC correction times. And they reported highly different numbers from like not detectable, so down to 0 nanoseconds to up to 10 milliseconds for ECC corrections. So this is what this bar here means. And then if we delegate to the operating system, this is where the disadvantage comes in, that we first have the overhead for the exception and the exception handler and everything. So this is why 2-bit flips take so much longer. And then for 4-bit flips, the actual correction time is bigger than the exception time. Yeah. And we can correct, so up to 5-bit flips in around a second, and 8-bit flips in almost reasonable 5 hours. So if your data is really valuable, you can wait for 8 hours to get your data corrected, maybe. But there's one problem I didn't talk about yet. The Mac is also stored in the DRAM, which means that a RowHammer attacker could also flip bits in the Mac. And if just a single bit in the Mac flips, we can search the data until the end of time. We will never find the data that actually matches the Mac because the Mac changed. And this is, of course, a problem. You have a question? Yeah.
I didn't want to talk about
Yeah,
that.
sure.
I had a question about the previous slide, actually.
Of course.
So did you also explore the option of like doing some periodic memory scrubbing and in case like some of these bit flips are accumulating over time, you know, like maybe you'll open and see like 3 bit flips and then again like 3 other bit flips instead of like fixing 6 bit flips, you can fix 3 bit flips twice.
We didn't do an analysis, but there are papers out there that looked at like naturally occurring bit flips in like a huge scale. I think there's a paper from some Google guys. It's pretty old at this point, but they looked at like how often do actual like just bit flips occur without an attacker, without RowHammer. And yeah, taking these numbers into account, one could do memory scrubbing with almost no overhead because it would be totally enough to like go through the memory once per day or even less than that. And then you find this low number of bit flips easily. So, but we didn't look at it further because you would need like to give a reasonable estimate on how often you should do it, or like you also need numbers how often do bit flips actually occur in the wild. And that's like, but I guess that proper systems do that already because the problem is even high with ECC. Like if you have ECC and you have bit flips accumulating, at one point you cannot detect them anymore, and then you have a big problem. So yeah, I think you have a short paragraph in the paper that talks about like memory scrubbing is of course makes sense if you want to keep the correction times low.
But during scrubbing you can also use Mac, right? Instead of ECC.
Yes, I mean in this case, yes.
Yeah.
Yeah, I mean if you use normal ECC and state of the art server CPU with ECC, you also have to do memory scrubbing to not have bit flips accumulate.
So I was curious, like, so in the doomsday scenario, I have 8-bit flips and it takes like 5 hours or 8 hours to fix it, right? So instead of facing that situation, is it possible I do like memory scrubbing using Mac every hour, for example?
Totally.
And then I will never see 8-bit flips, for example.
Yes, yes. You could easily implement this by just having a kernel thread that activates once per hour and reads the whole memory. It's like 20 lines of code, basically. And then you could do that. And then the chance is really low that you see 8-bit flips. Of course, if an attacker with RowHammer targets you, he's super lucky, then like memory scrubbing only helps against naturally occurring bit flips. If you have a RowHammer attacker, they can, of course, sync to your scrubbing. They detect that you scrub right now, and then they start and they have a full hour to accumulate bit flips, for example. And then it's not enough. But for naturally occurring bit flips, it makes sense. But then for naturally occurring bit flips, again, the chance that you see 8-bit flips is extremely low. Yeah. Basically not existent. So if I remember correctly, this Google paper where they looked at thousands of machines over multiple years, they had like a handful of triple or more bit flips, like millions of machine hours. So finding 8-bit flips is, you have to be really unlucky.
I see. Yeah. It needs to be really targeted using RowHammer or something.
Yes, yes, I think so. Yeah. Otherwise the chance is just too low.
Okay. Yeah, thanks.
You're welcome. So Macs can flip. Macs are stored in a DRAM, and that's a problem. And what we do, we don't check the Mac for equality, but just for approximate equality, because that's totally enough. So we allow a small number of bit flips in the Mac to be not the same and still let the data go through. And of course, we computed the security implications of that. There's this nice formula here. where we put in, for example, our MAC is 56 bits, and now we allow 3 bits to be different. Any 3 bits in this MAC are allowed to be different. This decreases the strength of our MAC from 56 bits to 41.2 bits. So just letting any 3 bits be different actually decreases the strength of our MAC quite a lot. And we did this math for a multiple number of bit flips, and we came up with this solution. So if we have 5 or less bit flips in the data, we have to do p MAC computations to go through to find the bit flip in the worst case, if you take all these 256 bits of data. And this gives us 2 to the power of 26 MAC computations we have to do. If we allow 3 bit flips in the MAC, we have this strength, and this number is still a lot higher than this number. And this means that the chance of a pre-image that we find 2 different data words with the same MAC is still extremely low. And if we look for more bit flips in the data, for example, if you look for 6 bit flips, we have to do 2 to the power of 31 MAC computations. And therefore, we only allow 2 bit flips in the MAC to be 2 bits in the MAC to be different. And again, we have high enough distance here. And up to 8 bit flips in the data, here we would have to do this many MAC computations. If we allowed 3 bit flips in the MAC, there would actually be a over 50% chance to find a second pre-image. So not the correct data, but some other data with a very similar MAC. So this is the number of bit flips we allow in the MAC to happen to still be secure. And we have some computations what this means for like what the chances are to actually find a second pre-image and break the data. But first, let's talk about software, because we delegated our correction to software because we can do more interesting things in software. And this is where this advanced correction comes in. As I said before, a lot of data in your DRAM, typically when your DRAM is like half full with your Google Chrome and stuff like that, all the other half that's empty is used by the operating system as page cache. So it just caches data from the disk in the DRAM for quick accesses. And if this data is corrupted, we can just reload it from the disk. And we have like also application binaries in there, shared libraries, memory map files, page cache, of course. The kernel itself is of course also there. So if we have a bit flip in the kernel code, we don't have to correct the code. The kernel is stored on the disk, just reloaded from the disk. There are other options. The kernel data, we know the structure of a lot of kernel data. For example, the code, as we said, we can reload it from the disk. Page tables, for example. We know how page tables look like. We know which page table, which bits in the page table are, for example, forced to be 0. If we do a brute force search, we don't have to check these bits. Or if one of these bits is 1 that we know they should be 0 in the page table, we just set this bit to 0 again, and we don't have to do the full brute force search. So just knowing about the structure of your data that you want to correct can help you a lot. For example, also task structs. We know for a lot of values, there are specific ranges that make sense and other ranges don't. So if we find corruptions in there, a lot quicker than a stupid brute force search, basically. And for page tables especially, there was another paper, I'm a co-author of pptx. This is a hardware design that protects page tables specifically. And there we looked at the page tables on a real running system. This was just some Ubuntu system. It had Chrome, Spotify, a few applications running. And there we see that a good 25% of all page frame numbers in page tables are contiguous. So if one page table entry is corrupted by RowHammer, we just look at the page table entry before and after and just try the page frame a number in between. And there's a really high chance, around 25%, that this is the correct page frame number and the data is corrected. We always use the MAC to check if this was actually the correct data. But yeah, 25%, we just take the next and previous page frame number and you're fine. Around 60% are just 0 PFNs. So if you find a corrupted page table entry and it's all 0 and there's 1 1 in there, it's really likely that the 1 is the bit flip. We set it to 0, the max match, and we are happy. And then there's a small percentage around, I think it was 12%, where we actually, it's not 0, it's not contiguous. And then we still have the known structure. We know some bits have to be 0, so we still faster than brute force search. And we also have the reverse page map, for example, that we could also use to reverse, like, to get the page frame numbers for specific virtual addresses. We're just going through the reverse page map. So having software that knows about the data that it's about to correct really can help us a lot. There's one problem though, and this is nesting. Let's take this example where a corruption exception comes in. The exception handler always first goes to the advanced correction scheme. It checks, is this data maybe on the disk? And if it's on the disk, reload it. So we don't do the correction as a search from the beginning because it takes too much time. We go to the advanced correction and see, can we do something with this data? Do we know something about this data? And here we are lucky. The operating system knows, oh, this corrupted data, it's stored on the disk. Perfect. Just reload it from the disk. Nice. It tries that, but then there's a problem. There's another bit flip in the ext4 driver of the operating system in the code. So it tries to execute the ext4 driver code to reload the data from the disk, and we get another corruption exception. Because now the operating system, of course, gets a corruption exception, and it wants to go to the advanced correction to check, is this kernel data? And then it sees, this is kernel data. Let's reload the kernel from the disk. It goes again in the ext4 driver. There's a bit flip in the ext4 driver. It gets a corruption exception. And then it checks, and so on. So it never exits this loop if a bit flip is in a bad position in the kernel code. So what we do instead is we detect this nesting and then directly go to the correction as a search. So if there's, for example, a bit flip in the ext4 driver, we cannot reload it from the disk because the driver doesn't run. So we have to do a correction as a search. And for this nesting detection, it basically looks like this in the exception handler. We have a special bit, but if it is set, it always does the correction as a search. If it's not set, it sets the bit, does the advanced error correction, that eventually does the correction as a search. If it doesn't find something, and it clears the nested bit again. And this means that 2 entrances in the exception handler never go here. The second one always goes here. And for this nesting bit, we have 2 requirements. We want to have it per process. So 2 processes should be allowed to run in parallel and perform correction in parallel. So we don't want the nesting bit to be shared between all processes. And we want it in a register, because if the nesting bit is stored in the memory, again, we have a problem with nesting if exactly this memory location is corrupted. And there's exactly 1 bit that fulfills both requirements, and that's the CR3 register, because it's per process and it's always in the CPU while the process is running. And it has a lot of unused bits in the top, and we just use one of those unused bits for the nesting bit. And then we can always detect nesting and never have a problem with that. And now to the final part of this design. It's the secure memory. This is where we put some code that it can always run no matter what happens to the DRAM. It's like CPU cache is a SRAM, so no RowHammer problem there, which is nice. It's 4 pages large because that's everything we need. We have to store the IDT and the GDT because the CPU always needs those to be able to execute and access data and code. By storing it in this secure memory, it can never be corrupted. This is great. We put the exception handler in there and the correction as a search. And therefore, these 4 things can never be attacked by a RowHammer attacker, and they can always run. And no matter how bad the memory is, it can always bootstrap back from there by correct as a search back the whole kernel or whatever it wants to do, if you've got time. Another problem is the yes?
Do we have to have this extra memory over there? Can't we put all this data into like our caches and pin them somehow so that they cannot be evicted?
Yes, this is actually what we proposed in the paper. I think ARM has actually a cache pinning extension. Yeah, one could implement it as that.
Okay.
Of course, it doesn't, the exact implementation is up to the designer if someone wants to implement that.
But it works as well.
Yes, it would work as well. Yeah, it has to be some memory on the CPU that,
Okay.
you could even, I mean, we also proposed for like, if you just have a smartphone CPU, for example, where you don't want this area overhead, you can also do it without that. Like the chance that an attacker hits one of those 4 pages is still extremely low.
Yeah.
So even without secure memory, the scheme would be pretty secure. And then again, worst case is denial of service. So, the other problem is the stack, because the stack can also be corrupted. When the kernel gets an exception, it reuses the stack from the process. And now an attacker could corrupt its own stack, access the stack, jump into the kernel, and then the kernel works with the corrupted stack. And to prevent this, we just increase the stack pointer by 256 byte for DDR5 and 512 byte for DDR4. So we always exit the region of the corruption. And that works pretty well. So this is how we can reuse the process stack without having to worry that the attacker itself corrupted its own stack or something like that. Yeah, and then we evaluated that. We built the whole thing in Gem5. Yes.
How do you deal with chip errors, hard errors that basically render the complete chip useless?
Yes, that's not supported. So this is
So this might be a private sort of question, but do you receive a lot of pushback on this?
Not really, actually. So one reviewer, we also have this in the paper, they wanted, actually apparently that's quite common, that a single connector on a DIMM is broken, so that if you read data, it's always the same location that's like wrong, or always leads to 0, always reads a 1. And we evaluated in the paper how we could correct this and how long it takes. But we made really clear in the threat model that like a full chip failing is not what you care about, because ECC also cannot do it. And
Chip kill can.
Chip kill, yes, yeah. But your normal ECC cannot do it.
I think when you say normal ECC,
if you get your Intel server with ECC, it cannot correct the full chip failing.
Server ECC should be able to correct full chip failing.
But that's 8 bits in a 64-bit word.
Yeah, should be not. There are schemes that can.
Yes. We cited the ECC exploit paper because they reverse engineered these schemes, and at least the schemes they reverse engineered were not able to do chip kill correction. Yeah. And so this is what we just wanted to be like better than ECC. If chip kill is your threat model, then of course chip kill also works.
I mean, don't like suddenly have to shut down the whole system. You can still tolerate errors, especially if it's just a few, maybe one. Ideally, just one bit that's always wrong. Then you can just correct it.
Yeah, exactly. If it's just one bit that's wrong, the system keeps working as usual.
The problem is like the error could happen in one of the control pins as well, and then that chip is like useless at that point.
Yes, then CSI Rowhammer fails. Yeah. Exactly. So chip kill not supported, not part of the threat model. We implemented this whole thing in Gem5. It was a great fun. Great master thesis. We modified the Linux kernel to add the exception handler and everything. And in Gem5, we actually first had to implement ECC memory, so memory with a broader bus and the additional bits. And then we modified the memory controller to do the MAC computation and added the exception and everything. we modified the Linux kernel to handle the exception and do the correction as a search. And with this, we evaluated the correct functionality. So we induced bit flips in our GEM5 model, and it was able to detect and correct them. And we also evaluated the performance overhead. So we correctly modeled the time it takes to compute the MAC on the data. And this is what we got. So the worst performance overhead we see is this benchmark, the OceanCP. Yes. And the interesting thing here is that it has approximately the percentage overhead that corresponds to the time it takes to compute the Karma MAC. So we say on average, it takes 100 nanoseconds to access the DRAM, and our MAC computation takes around 5 nanoseconds. So 5% is 5% of the additional time for the DRAM access. And here we see a little bit less than 5% performance overhead. So if your application is memory bound, you directly see the impact of the MAC computation. For all other benchmarks that are not memory bound, the performance is lower. So we can give an upper bound for the performance impact with this scheme. And yeah, for some applications that are just compute, we see almost no overhead, and there are then some applications in between. So 5% in the worst case. We did a security evaluation.
So it increased memory access latency, but it's not too bad actually, right? So, I mean, one can also choose to replicate some of these components in their architecture. And then you can read a chunk of memory, for example, you do the MAC computation over there. And then you like at the same time you access to another location memory, and then you start another MAC computation. So you can overlap those latencies.
Yes.
To provide more bandwidth.
We didn't model that, but that would be possible, yes.
Okay.
Yeah.
That would be nice.
Yeah. Interleave different, like the combinations of different memory accesses, which we didn't do. And this would probably, yeah, maybe half the latency in the best case, but something like that, yeah. But we also, yeah, we'll talk about the speculative execution shortly.
Sure.
That would have no performance overhead. Yeah, we did a security evaluation, especially of this approximate equality, because not comparing MACs that they're exactly the same. Most people don't like that, but we showed that it's actually doable if you don't allow too many bits to be different. And then we computed based on data of other papers that looked at silent data corruption in like naturally occurring bit flips in huge server farms. We computed that silent data corruption actually happens less than once per 10 to the 9 billion years. So pretty much never. And an extremely successful RowHammer attacker that is able to flip bits every 128 milliseconds. So multiple bit flips per second for a full year straight has a chance of finding a secondary image of this like 10 to the power of 10 times, yeah, 10 to the power of minus 4%. And this means that the RowHammer attack is able to find any secondary image. This doesn't have to be usable data for the attacker. So also, yeah.
Maybe you finish.
Yeah, so also this super skilled RowHammer attacker is extremely lucky, finds extremely broken DRAM, has a really low chance of actually exploiting this.
So I was going to ask about this table actually. You have max length set at 41.2.
Yes.
I was wondering if this changes during runtime. So should we perceive this as something that's kind of adaptive, or? No,
this is the thing I showed before.
Yeah.
Yes. Yeah. So no, we just when comparing the max, we basically what we do is we XOR the two max, and then we do a pop count to see how many ones we get. If the max are equal, everything is 0. And if we look for 5 or less bit flips, we allow the pop count to be up to 3. So we just allow any 3 bits to be different.
But do you know how many bit flips you have? So can you make this decision on runtime, or should you?
Yes, because we check in software, we check for 2 bit flips, right? And then we do this with d equals 3. And then we don't find the correct data because there are probably more bit flips. So we do it with 3, with 4, with 5. And we still didn't find the correct data. So when we then try 6 bit flips in our brute force search, we reduce D to 2.
Okay.
So it happens on the fly while trying different number of bit flips, because this is the actual number of MAC computations we then perform in the worst case. And therefore, we have to reduce this number to not find secondary images.
Yeah.
Yeah. Yes. So, and then we have some final notions. We fully support virtual environments in this design. This was one of the major vision criteria to show how this works. And we actually showed that we only require host support. The whole system would be able to run without the guest knowing about CSI Rowhammer. In this case, without all the advanced correction schemes, because the host doesn't know what's going on in the guest. But we also imagine a system where the guest also knows about CSI Rowhammer, and then the host could give the exception to the guest, and then the guest can do its own correction. That would totally work. So guest support is optional. And that would make upgrading an existing system from ECC to, for example, CSI Rowhammer quite easy, because all your virtual machine guests don't have to support it. We also showed the upgrade path from, like, if in a CPU that supports ECC and CSI Rowhammer, and how operating system could then switch if it supports CSI Rowhammer, for example, something like that. What else do we have in the paper? So we are able to correct errors from a faulty DIMM connection. The CPU die area overhead is tiny because we only have a few comma block cipher blocks and this secure memory, which is only 4 pages large. We are compatible with TRR, and we also just suggest using a system like CSI Rowhammer together with another hardware-based mitigation, because modern DRAM wouldn't work anymore without TRR. It needs some hardware-based solution to get rid of most of the bit flips. But then if bit flips slip through, or we have something like half-double RowHammer that actually breaks TRR, then CSI Rowhammer comes into play and fixes the remaining bit flips. And this can also be used with memory encryption, for example. Yeah, and what possibilities does this open up? This is back to the argument why we want to do something like this in software, because doing correction in software opens up many possibilities. One could imagine a data correction as a service cloud provider where you just, I don't know, my private key is corrupted. I give it to this service, it corrects my private key and then gives it back to me, something like that. One could also do a data correction by ChatGPT, because AI can do everything nowadays, right? So I asked ChatGPT, find the error in test message, maybe found it already, so that it produces the following SHA-512 hash. I gave it the hash, and then it actually, this was still GPT 3.5, it actually gave a quite reasonable answer that, like, this is a hash function, it's a one-way function. Yeah, it's not possible to determine that, which is kind of correct. Yeah, it would have been able if it thought a bit more. So I tried, can you just brute force the correct answer for me? And apparently there are some content policies that don't allow that, sadly. Yeah, so not fully working yet.
You should have said, can you try hardware?
Please. But now to some serious things one could do. One could have hardware acceleration. So going from the single bit flip correction in hardware to the software and then back into hardware would make sense if you think about it like that. This was one of the biggest dies when we wrote the paper. It's like 600 square millimeters, a huge die. And this fits roughly 500,000 karma blocks. So you can compute max very parallel on this die if you would fill it only with karma blocks. And this would reduce the correction time for 8-bit flips from the 5.4 hours you get with a single karma block to 40 milliseconds. And 40 milliseconds is quite reasonable. Like your computer hangs for a short time, you corrected 8-bit flips. But of course, we don't want to have a huge die only for correction in every laptop. There would be a huge waste of time. But one could imagine a system where you have a huge server farms. These 8-bit flips, they happen basically never. So we have just a single specialized node, for example, bit flip correction, just brute forcing bit flips. And when it doesn't happen often, when a server has 8-bit flips or more, it sends it to this node. It crunches the numbers and returns the result. We could also reduce the performance impact caused by the MAC computation, because all the performance impact of CSI Rowhammer in a system that's not under attack comes from these MAC computations. So it would be possible to transiently execute without verifying the data. So when the CPU requests data, it gets it in, it starts computing with the data, and in parallel verifies the MAC. This would mean we have no performance overhead if the MACs always match. But of course, we have transient execution with maybe corrupted data, but there are papers out there, besides the two, that actually showed that it's possible to have secure execution of unverified data. So with a system like this, there would be no performance overhead on a system that's not under attack. Would be pretty neat. The last thing, which is also a nice side effect of CSI Rowhammer, some mobile phone vendors had a great idea. With low power DDR4 memory chips, they introduced on-chip ECC. And this is great, because if you have on-chip ECC, you can detect and correct some bit flips. So we can now simply reduce the voltage and correct potential bit flips. So we reduce the voltage to a level where we know that bit flips are coming up, but we save a lot of power and have a longer battery life. And we just use ECC for that. But that basically means that ECC doesn't give us any security benefits. So we used ECC only to save energy, but we are still not secure. That's bad. And double bit flips are uncorrectable, even undetectable on on-chip ECC. So we didn't win anything there except a bit longer battery runtime. If CSI Rowhammer, you can do this a lot better, because if the DRAM or the CPU comes with CSI Rowhammer, we can now reduce the voltage again and correct potential bit flips, but there is no chance that we have uncorrectable or undetectable bit. Uncorrectable maybe, but we don't have any undetectable bit flips. So the security is always guaranteed. We'll never have bit flip that break the system. And too aggressive optimization hurts the performance. This means if a mobile phone manufacturer undervolts the DRAM too much, it gets too many bit flips, and actually the performance decreases again. And also the power consumption increases again, because now CSI Rowhammer has to do a lot of corrections, brute force corrections. So with this, you actually have a sweet spot for energy savings without always hurting security. Security is always guaranteed. So that's what CSI Rowhammer could also be used for. And with this, I'm already at the end of the conclusion. RowPress and RowHammer effects can overlap. This was the result of our latest paper. And we actually don't know exactly what's going on there, sadly, yet. Many Rowhammer mitigations focus on characteristics and can therefore never guarantee security, because we never know if a new effect is coming up that breaks these. And therefore, we should use something like a MAC to ensure data integrity in all cases. And having a software-based correction together with hardware-based correction actually opens up many possibilities what you can do to correct data. Yes. Thank you very much. If you want to read the paper, there are the QR codes directly to the PDF. You should try it. It's not dangerous. Any questions?
So I can make a comment about undervolting at the end.
Mm-hmm.
So I did a lot of experiments actually with like reducing voltage for DRAM chips. What we observed in general was so you reduce voltage down to some level, which is like still within the guard band, and you don't see any bit flips.
Mm-hmm.
Let's say you reduce from like 1.3 volts, 1.2 volts down to like 1 volt. You don't see any bit flips. And then you see a few bit flips at that point. If you increase your access latencies, it's already enough to like avoid those bit flips in most cases. But then if you try reducing it like a little bit further down, let's say you go from 1 volt to like 0.975 volts. Yeah. It's just like a little bit reduction, right? And then you see bit flips all over.
That's
So
interesting.
Yeah, it increases quite significantly all of a sudden.
Yes.
So it can
That's
be a
cool.
bit challenging for that kind of.
Yes.
idea, I guess.
Yes. I think what you're saying now is that the garbage are there for no reason. And that's probably not the case.
Yeah.
So-
I'm not saying that's not.
Yeah. So
reason.
they probably put the garbage there for aging reasons, for example, or temperature or stuff like that.
Yeah.
So if you reduce the voltage to a level where it works now, of course, there's no guarantee that it will work next year.
Yeah.
So what these manufacturers did, they didn't decrease it like to the absolute minimum where it works straight out of the factory, because then every phone would probably break after a year. But still, they did stuff like that.
Yeah, so one pushback actually for those works was like you do this characterization once, you find out the guard band, it's the guard band today, and then tomorrow it can be a different guard band. The
Yes.
characteristics can change.
Yeah, this is why they put the huge guard bands.
Yeah.
So I don't know about DRAM, but we just published a paper about CPUs
Yeah.
and undervolting, and there we looked a bit into that.
Yeah.
I know that for CPUs, they actually measure the voltage requirement on each boot. So they have some aging circuit in there that always runs while the CPU is running, and they measure the latency of this circuit on every boot to know how much the transistor already aged, the transistor is already aged, and then modify the guard band based on this aging prediction.
So it's
circuits.
sort of like a sensor for that.
Yes. So they just have a lot of inverters and just measure the latency to know how long was the CPU already running, how much did it degrade.
Yeah.
And maybe they do something like that in DRAM. I think with DDR5 they could do it, right? They have the voltage converters on the board, so they could actually modify the voltage quite directly and based on
Yeah,
aging.
I think so.
Yeah.
I was gonna say like you can also use Mac as like a canary, I guess, because you detect like how many bit flips happen, right?
Yes.
You can reduce the voltage until you see bit flips, and then you can stop reducing.
Exactly, and then you could also do this dynamically, I guess. And
Yeah.
as a system on a chip, so you control the DRAM voltage.
So it accounts for aging. Let's say.
Yeah.
I didn't know that you were an author and half double as well.
Yes, there was actually my master thesis, the exploit.
And PT learn as well.
Yes.
Collaborate a lot.
Yeah. Any questions from YouTube?
No.
Perfect. Yes.
Should RowHammer be sold by DRAM manufacturers or system designers or someone else?
I mean, the best case would be DRAM manufacturers. It's their fault, but it didn't work too well in the last 10 years. So yeah, maybe they managed with DDR5.
Yeah.
Who knows?
Do you know about PRAC or crack, this new mitigation?
Yes, not in detail, but it sounds promising, I would say. But yeah, I'm still waiting for a DDR5 RowHammer paper to come out. Someone must someone must do it.
There's one coming like in 2-3 weeks, right? Zenhammer. It already shows.
Yes, but it's a tiny number, right?
It's a tiny number, yes.
Yes.
But it shows that it's possible.
Yes. And we don't know if they use all the mitigations, because I think PRAC is not mandatory in DDR5, right? So yeah, you can probably find some bad modules that still only do the minimum required mitigations, and then
True.
So I guess regardless of what they implement, some bits will flip. So
yeah.
that's where CSI can be useful.
Exactly. This was our proposal. So you can, I think it's hard to guarantee not a single bit flip, never, in hardware. You always have process variation. You maybe have this one chip that slips through while testing in the fab, and then it's just like, I don't know, a year of aging. We don't know about aging exactly, but this could be the case. Then it starts flipping, who knows? Yeah. So having something like this, some form of integrity protection for the few bit flips that are never able to be resolved would be nice.
Have you thought about how to apply this to other memory, like DRAM technologies that don't have multiple chips necessarily, like HBM?
Not really, but it would work for HBM. It's a single chip, but you still have the same memory layout, I guess, like the same data bus width and everything. And if you have HBM with ECC, which probably exists, you can do exactly the same thing.
I think it even makes more sense there right now because of this hard error stuff.
Yes, yes.
Chip kill and HBM
Mhm. Yeah, that's true. If your chip dies, then you're done anyways. Yeah.
I'm really interested to see like this, all this like integrity check mechanism is implemented in the memory itself.
Mhm.
It can be a kernel in a PIM core. It can be some like hardwired logic there. Yeah, it will be really interesting to see the trade-offs there.
Yes, that would be cool. The Karma block cipher itself, the hardware design is tiny, so it would definitely fit. Mhm. It would be
Maybe there's
interesting.
a follow-up paper there. I don't know.
Yeah, maybe compute in DRAM style-ish, or at least close to the DRAM. Yeah, and then you just need some signal to tell the CPU or the operating system that it was like uncorrectable or something like that.
Mhm.
Yeah. I would probably, yeah, it would definitely increase performance. You don't have to get all the data to the memory controller before committing the MAC. If you do it directly on the DIMM, you have the data readily available, and then probably could shave off some percentage in overhead there.
So let's say you detected that there are like some bit Phillips in the kernel, Linux kernel, or I don't know, something that is already like that has a copy in the disk.
Yes.
So you mentioned that you can just fetch it from the disk, right? How long does it take to fetch the whole Linux kernel, for example?
I mean, you know where
tiny, right?
the Linux kernel is quite small.
Yeah.
It's zipped on the, I think this is gzip to make it even smaller. So you just load it into memory, unpack it, and then you basically just have to swap out the part that's corrupted. Yeah.
I see.
Yeah. So it will probably take, I don't know, microseconds.
Okay.
Probably, maybe a millisecond.
So we discussed this a bit, the denial of service attack based on CSI Rowhammer. You don't, not interested in getting 8-bit flips because it just takes, it's impossible almost.
Yes, yes.
But can you do a denial of service based on the advanced correction? Like, could you repeatedly use the bits of the kernel there?
By increasing the scale?
What's that?
I know what you mean.
Yeah.
So we didn't describe it in detail, but we wrote something that the operating system should still have some mechanism to prevent like repeated bit flips. It's enough to like, if you find, if for example, some memory location is corrupted once, then corrupted again. We talked about, so one solution would be to have some correction cache that just caches the last 10 corrections. And if it finds the same correction again, it just like, it knows the physical address. It just does the same correction again, flips the 1 bit and it's done. Or again, if the operating system knows about all the corruptions that happen, it could also just remap the physical page of some process. It doesn't have to kill the, doesn't even have to kill the process, just remap, shuffle the pages, for example, the physical pages, and then the aggressor pages are not hammering anymore, anything specific. So it would be quite simple to do that. You could even just, if you detect some attack, just shuffle all the physical pages. It's a short delay, but then all the attacks are basically stopped. For example, I mean, it's a quite stupid solution, but it would be a solution.
Yeah. And it's very unlikely for someone to remember a kernel page or
Yes, that's already pretty difficult. The kernel is mostly mapped as 2 megabyte huge pages. So you don't get neighboring rows like in between. So you only get like, you for 2 megabyte pages, you can't do double-sided RowHammer. And that already makes it difficult. So there's low chance, yeah. And then you also have to get physical pages close to the kernel, which typically doesn't happen. So unlikely. This is also why I said the secure memory is required for like a 100% guarantee. But if you don't have that and you just have these 4 pages somewhere embedded in 2 megabyte kernel pages, there's like pretty much no chance that someone actually hammers them.
Also, at the same time, then it means you don't really need the advanced version to go with that.
For the kernel, yes, yeah.
For other things, though.
Yeah. That's up to the operating system programmers then to decide if it makes sense to implement it or not. Yeah. Then we just wanted to show what would be possible. Yeah. Okay, then thanks for your attention. Thanks for having me. Thanks to the people from YouTube.
They're also thanking you.
Oh, perfect.